Today we are going to do the graphical representation of motion. Now, a graph is basically a mathematical tool which is used to describe anything, okay? A data basically. In physics, we apply it for distance time, we can apply it for velocity time. In this chapter, such graphs can be drawn. So, the very first graph which we are going to discuss and learn today is the distance time graph. Now the distance time graph is basically a graph which shows the variation of the distance covered by an object to the time taken by the object. The time is always taken in the x-axis as I am making right now. This is my x-axis, and the distance is always plotted on the y-axis. We have to put the namings of x and y whenever we plot a graph. Now, just for our convenience, from the origin, we mark 1 centimeter each on the time axis. Similarly, 1 centimeter mark on the distance axis. Time is denoted by the letter T with its SI unit of seconds and with an arrow mark that the time is going towards this 1, 2, 3 and so on. Similarly, for the distance we denote the distance with letter S. We call it distance time graph, but when we denote the distance, it is denoted by small letter S. Similarly, time is denoted by letter capital T. Now, the SI unit of distance is meters, denoted by small m and an arrow. Now, when we need to plot the very first case, the case when the object is at rest. Rest means with respect to the reference point, the object has not moved from its distance. It is continuously standing on the same position. So, for example, if I take the distance of the object from the origin to be 4 meters. So at 0 seconds, that means like no time, it was at 4 meters. Then in the first second again, it was at 4 meters. Second it was again at 4 meters. Third second also it was at 4 meters. That means the object is not at all moving from its position. And when we connect these dots, we get a straight line which is parallel to the x-axis. We get a straight line parallel to the x-axis, and this is how the distance time graph for a resting object is plotted. Now, the second graph in the distance time graph which we are going to do is for the object which is in uniform motion. Now, uniform motion, as you all know by now, that it is a motion in which an object covers equal distance in equal interval of time. Now, such a thing when we need to plot it in a graph, first the basic rules again, that will make the y-axis, will make the x-axis, one centimeter as a gap to mark the seconds, and 1 meter as 1 centimeter as a gap to mark the distance. From the origin, we write down the numbers. Again, the x-axis as denoted is time, letter T, small letter second, its SI unit, and then a small arrow. Similarly, distance, as I told you in my previous video also, that the distance is denoted by a small letter S, SI unit is meters, and a arrow. Numbering to be done. Now, again, if I repeat, uniform motion says that equal distance is covered in equal interval of time. Let's say that the object is covering a distance of 1 meters in 1 second. So, when we plot the graph for 1 meter in 1 second, when we need to mark a point on the graph which tells us that the object has covered 1 meter of distance in 1 second of time. So here is my object. Now after 2 seconds, the object has covered 2 meters given by in the y-axis and 2 seconds given in the x-axis. So here I get my position of my object. In the third second again, the object is covering 3 meters. So I get the point here. And I'll plot it like this for 4 meters in 4 seconds. Okay. Over here. Now, in your previous graph, if I show you, we connected the points to get the graph. Similarly, in this one also, we'll connect these points, these dots to get our graph. And if you look closely, that we are getting a straight line graph from the origin. All my points are lying on the origin, on the graph. Now this line over here which we got by connecting the dots is called as slope. The detail of this slope you will be studying in class 10. There is a chapter of trigonometry in mathematics. The details will be in that chapter. Just for briefing, slope is the name of this particular line. Whatever we plot in a graph is a slope, okay, against the values of the y-axis and the x-axis. Now the slope over here, since we have got a straight line, this slope, the line name is slope, we are going to calculate the value of this line. The value, by when I say the value of this line, that doesn't mean the actual measurement of this line. We are not going to use the Pythagoras theorem at all to determine the length of this slope. We are trying to do the calculation for the slope, to determine the value for the slope and not the actual length of the slope. So no Pythagoras theorem will be used in it. So to determine the slope, and the slope in a dt graph for a uniform motion tells us about the speed. So the slope, if I calculate, it will actually tell me about the speed of the object. So I need to take 2 points and make a right angle triangle. Alright, this is my right angle triangle and this is the part of a slope I am taking to calculate the speed. Now to calculate the speed, again I will repeat, I will not be doing the Pythagoras theorem or calculating the actual value of Pythagoras theorem. I need to know what these points on my distance and my time is reflecting. Now the distance at this point is reflecting, for point A it is reflecting 4. For point A on time axis it is reflecting 4. At point C it is reflecting 2 meters and time is 2 seconds. Whenever I need to calculate the slope of a graph, the formula for slope is perpendicular by base. Again I am saying it is not the actual length of the perpendicular. You will not take a scale and start measuring what is the length of this line. We are not doing the Pythagoras theorem here. We just need the value of what is the value of this perpendicular and what is the value of this base. So if you say the perpendicular AB, it is reflecting to 4 and 2. So if I name it as y2 and y1 and these as x2 and x1, so I can write my perpendicular height is y2 minus y1 and my base, if you see my base is representing x2 and x1, so x2 minus x1. If we solve it further, what is the y2 value? The y2 value was 4 over here and y1 value is 2 over here. Similarly, my x2 value is 4 over here and x1 value is 2 over here. In many books, you may get this formula. This y2 minus y1 upon x2 minus x1 also written as s2 minus s1 upon t2 minus t1. Since s and t, I told you previously that these are the denotions for the distance and the time. So therefore this formula can also be written in this way. So it depends on the book which you are referring for your studies. So when you calculate 4 minus 2, you get 2 and again 2, which gives you 1. Now S2 or Y2, the SI unit is meters and division is time. So meter per second. And this is how we calculate the slope of a uniform motion, which actually gives us the speed, and a uniform motion will always have a straight line like this. Now the third graph in the distance time graph is for an object which is moving in a non-uniform motion. My third part of this DT graph is non-uniform motion, object in non-uniform motion. Now non-uniform, as per definitions, as we have learned by now, that an object is said to be having a non-uniform motion when it covers unequal distance in equal interval of time. So the basics again, as I repeat, that we have to draw the graph and with 1 centimeter as the measurements, we'll do the timings. Over here also 1 centimeter each will give me the measurement for the distance. So numbering it, and going ahead, we need to write down S, denotion for the distance by its SI unit and a small arrow, with Y and X to be written, also time in seconds and a small arrow to be done. Now when we say that it is not covering equal distance in equal interval of time, suppose my object in the very first second, in the very first 1 second, it travels 1 meter only. So my point is over here, but in the second second, it is still at 1. That means it has not moved even a distance from its initial position at the 1 second. Then at the third, it moves to 1 meter more. So my point against 2 meters and 3 seconds. Thereafter, my object moves. In the 4th second, it moves to 4 meters. So if we plot it with the scale, we get it like this. And in the 5th second, it is again covering 1 meter against the 5th second. So this is how my graph is going. So if I plot it, if I plot my graph, I don't get a straight line, but I keep on getting different lines. So with much closer points, okay, on this graph, like even microseconds if we take, with much closer point, this zigzag shaped graph can either, I'll plot it one more for you, can either become a graph like this, or it can also become a graph like this. So whenever a curved graph is plotted in a distance time graph, it always shows that the body is in non-uniform motion. Now whenever such data is given to you that unequal distances are being covered in equal interval of time, and you plot it like this, you get usually a curve which is not a straight line, and we can only have a straight line only in, as we have done earlier, we can get a straight line only in a uniform motion, but not in a non-uniform motion. A non-uniform motion will always have a graph like curve.